What if I told you that different mathematical tools can reveal hidden details about the same system? As an engineer, this has an effect on how you might design something or validate that it will function as you intended. You may have a system that behaves as designed for a specific input. Here you can see that a target output has been set, but the response might overshoot and oscillate. Or it might converge quickly and have very minimal error. But consider what would happen if, for example, the frequency changed. Would it still behave in the same way? How would you analyze this? In this video, you will see how there are 3 key tools that are often taught individually but are most meaningful when used together. These tools are the Laplace, Fourier, and Z-transform. Combined, they give a picture about both analog and discrete versions of a system that can be related back to time domain and frequency domain response. This is incredibly important when trying to apply control theory practically. This video won't go into too much detail on control theory, but it will allow you to have an appreciation for the topic and provide an introduction to one of the most fascinating areas of engineering. Let's start with the Laplace transform for analog systems. The rule is very simple. Apply the transformation by taking an equation and passing it through the integral shown. By analyzing common patterns, there are a few basic rules that can be applied. You should see that a differential equation can be transformed into an algebraic equation in terms of the Laplace variable s. This differential equation describes the motion of a mass spring damper system such as a car suspension. We can apply the Laplace transform and assume no initial conditions. It can now be rearranged into the ratio of output to input, called a transfer function. The roots of the denominator polynomial are called poles. These are complex numbers where the y-axis is imaginary and the x-axis is real, although you don't need to know much about complex numbers here. To see why they are important, we will solve the ODE in the traditional way and compare this against the pole locations. A step response has been applied to the system. This is like modeling the car passing over a bump in the road and the suspension trying to keep the vertical position of the car under control. The pole location influences whether the system is stable, unstable, or subject to pure oscillation. Gain-based control is performed by a multiplication factor on the transfer function, and it causes the roots to follow a path called the root locus, as you can see here. If at any point the root goes into the right half plane, which is the unstable region, it can cause instability. What this means practically is that the car may oscillate in an uncontrolled manner until something breaks, and as you can see, it wouldn't be very comfortable for the driver. Different controller types seek to change the shape of this graph to keep it in the left half plane, as well as tailoring the transient nature of the step response, with the aim of reducing the effect of the input. This is done by using a feedback loop, which is essentially telling the system how well it is meeting a target so that it can adjust itself. So why use a Laplace transform? We consider a transfer function as a block. In the time domain, the effect that a system has on an input is represented by a mathematical convolution. However, when taken into the Laplace domain, this tricky convolution becomes a multiplication of transfer functions. This allows controllers and multiple systems to be connected together. With stability much easier to analyze as the combined transfer function can be found from multiplications and a few simple rules. As usual in maths, we transform our system to a form that is easier to work with. So rather than calculus, you can think of systems in terms of block diagrams with transfer functions. Here, we can see a simple open-loop block diagram with its equivalent transfer function. We can also have a closed-loop block diagram. When we talk about controllers, we are referring to a block that can be added to change the system for stability and performance purposes. When we add other types of controllers, the order of the system increases as the controller adds poles to the system. This is manageable as we can still find the polynomial root with numerical methods, but higher-order ODEs are much harder to work with in the time domain. Next, we will move on to the Fourier transform. The Fourier transform applies to non-periodic signals. The idea is that any signal can be made up of a summation of signals of different frequencies. This transformation allows us to see how much of each frequency component is present in a signal by giving an equation in terms of the frequency variable, f. This allows knowledge of the magnitude and phase of each frequency component within a signal. Then, it can be put into a graph called a Bode plot so that we can see the magnitude and phase response of a system. The magnitude and phase can change with frequency, so the answer to the question from earlier is no, the system won't behave the same with different frequencies. In the context of the car suspension system, the input signal is the road surface. The magnitude peak refers to the frequency at which the oscillation amplitude grows and causes an effect called resonance. This can be seen here at certain frequencies, called the resonant frequencies. The issue is that it can cause excessive damage to systems and stop them from functioning as intended. Controller or filter design can be based on the frequency response, aiming to shape the resulting graphs to get the correct stability. Alternatively, we could have designed a control system to get a certain step response according to the Laplace transform. If you think about the Laplace and Fourier transforms, they are the same when S equals j omega, so we can make a substitution and obtain the magnitude and phase relationships. Although the resulting equation will probably look complicated, it is just a complex number that can be arranged into x plus yj format, and the magnitude and phase obtained from this. We can check if our system has any frequencies that introduce unwanted behavior and then take action accordingly. The Z-transform is used to convert our thinking towards a digital version of the system. Although there is a lot of theory for the Z-transform, the most directly useful application is based on our system, either in the Laplace domain or frequency domain. Why would we want a discrete version of our system? The answer is that in engineering, most of the time we may have a sensor connected to a microcontroller. Sensors take samples, but the act of sampling is not continuous. It is discrete. So the question is, how do we implement our continuous controller in reality? The definition of the Z-transform is shown here, along with the conversion from Laplace domain to the Z domain. This conversion is just an approximation of what is known as a conformal mapping. Consider a transfer function that obtains the derivative of an input. It is represented by the Laplace variable s. We can apply one of the mappings and then rearrange the equation. By considering the definition of the Z-transform, we can undo it to obtain the difference equation. Notice that the terms refer to current and past values only. All we now have to do is code this into a microcontroller and end up with our control signal that can be sent out to an actuator. Here are some examples of an input signal being passed through difference equations. You can see the input signal being applied, and then 3 different types of filters. The first one is a high-pass filter. The second is a differentiator, which is based on the difference equations derived previously. The ability to calculate the derivative of a signal in real time is very useful for derivative-based controllers. The last is a moving average filter, which can be used to smooth a signal in the event of high-frequency noise. The nice thing about this is that you only need the previous samples to update the next output value, and so it can be used in real-time applications. The Z-transform is not the only way of realizing a control system, but it allows you to use digital signal processing techniques without requiring strong knowledge of mechanical or electrical systems that would be needed for analog design. You should now be able to appreciate the role that these mathematical tools play in systems engineering and how they should be used as a complete package, and not just individually. Like and subscribe to this channel for more, and if you want to see more detail on any aspect of this video, let us know in the comments.